Here's a visualization of the error function. We're standing on top of a mountain, Mount Everest, and we want to descend. But it's not that easy because it's cloudy and the mountain is very big, so we can't really see the big picture. What we'll do to go down is we'll look around us and we consider all the possible directions in which we can walk. Then we pick a direction that makes us descend the most. Let's say it's this one over here. So we take a step in that direction. Thus, we've decreased the height. Once we take the step, then we start the process again and again, always decreasing the height until we go all the way down the mountain, minimizing the height. In this case, the key metric that we use to solve the problem is the height. We'll call the height the error. The error is what's telling us how badly we're doing at the moment and how far we are from an ideal solution. And if we constantly take steps to decrease the error, then we'll eventually solve our problem, descending from Mount Everest. Some of you may be thinking, wait, that doesn't necessarily solve the problem. What if I get stuck in a valley, a local minimum, but that's not the bottom of the mountain? This happens a lot in machine learning, and we'll see different ways to solve this later in the NanoDB. It's also worth noting that many times a local minimum will give us a pretty good solution to a problem. This method, which we'll study in more detail later, is called gradient descent. So let's try that approach to solve our problem. What would be a good error function here? What would be a good way to tell the computer how badly it's doing? Well, here's our line with our positive and negative area, and the question is, how do we tell the computer how far it is from a perfect solution? Well, maybe we can count the number of mistakes. There are 2 mistakes here, so that's our height, that's our error. So just as we did to descend from the mountain, we look around all the directions in which we can move the line in order to decrease our error. So let's say we move in this direction, we'll decrease the number of errors to 1. And then if we move it in this direction, we'll decrease the number of errors to 0. And then we're done, right? Well, almost. There's a small problem with that approach. In our algorithms, we'll be taking very small steps. And the reason for this is calculus, because our tiny steps will be calculated by derivatives. So what happens if we take very small steps here? We start with 2 errors, and then move a tiny amount, and we're still at 2 errors. Then we move a tiny amount again, and we're still at 2 errors. Another tiny amount, and we're still at 2. And again and again. So not much we can do here. This is the equivalent to using gradient descent to try to descend from an Aztec pyramid with flat steps. If we're standing here on the 2nd floor for 2 errors, and we look around ourselves, we'll always see 2 errors, and we'll get confused and not know what to do. On the other hand, in Mount Everest, we can detect very small variations in height, and we can figure out in what direction it can decrease the most. In math terms, this means that in order for us to do gradient descent, our error function cannot be discrete. It should be continuous. Mount Everest is continuous since small variations in our positions will translate to small variations in the height, but the Aztec pyramid is not, since the height jumps from 2 to 1 and then from 1 to 0. As a matter of fact, our error function needs to be differentiable, but we'll see that later. So what we need to do here is to construct an error function that is continuous, and we'll do this as follows. So here are our 6 points, with 4 of them correctly classified. That's 2 blue and 2 red, and 2 of them incorrectly classified. That is this red point at the very left and this blue point at the very right. The error function is going to assign a large penalty to the 2 incorrectly classified points and small penalties to the 4 correctly classified points. Here we are representing the size of the point as the penalty. The penalty is roughly the distance from the boundary when the point is misclassified, and almost 0 when the point is correctly classified. We learn the formula for the error later in the class. So now we obtain the total error by adding all the errors from the corresponding points. Here we have a large number since the 2 misclassified points add a large amount to the error. And the idea now is to move the line around in order to decrease this error. But now we can do it because we can make very tiny changes to the parameters of the line, which will amount to very tiny changes in the error function. So if we move the line, say, in this direction, we can see that some errors decrease, some slightly increase, but in general, when we consider the sum gets smaller. And we can see that because we've now correctly classified the 2 points that were misclassified before. So once we are able to build an error function with this property, we can now use gradient descent to solve our problem. So here's the full picture. Here we are at the summit of Mount Everest. We're quite high up because our error is large. As you can see, The error is the height, which is the sum of the blue and red areas. We explore around to see what direction brings us down the most, or equivalently, what direction can we move the line to reduce the error the most. And we take a step in that direction. So in the mountain, we go down one step, and in the graph, we've reduced the error a bit by correctly classifying one of the points. And now we do it again. We calculate the error. We look around ourselves to see in what direction we descend the most. We take a step in that direction, and that brings us down the mountain. So on the left, we have reduced the height and successfully descended from the mountain, and on the right, we have reduced the error to its minimum possible value and successfully classified our points. Now the question is, how do we define this error function? That's what we'll do next.